Okay, so correlation. So in this example here, a shop manager thinks that the number of ice creams sold at his shop on a particular day is connected to the temperature. So he wants to know if there's a correlation between the number of ice creams and the temperature. Okay, so he's trying to work out basically if the temperature increases, does the number of ice creams sold increase, which would make sense. Okay, so what he's done is for different days he's collected the temperature and the number of ice creams sold. Okay, so he's done that for 1, 2, 3, 4, 5, 6, 7, 8, 9 days. Okay, and obviously one thing we can do is to put those results onto a scatter graph. Okay, so here we have the temperature along the bottom. Let me just go a bit smaller. The temperature along the bottom and the number of ice creams sold on the y-axis. And you can see there does look like there is some good correlation. Now, generally, we're looking for linear correlation. That's for the one we're going to do first. But there are obviously other types of correlation. But at the moment, yeah, let's think about this one. Obviously looks like it's a straight line, so linear correlation. Okay, now this is just a review then of the types of correlation. Obviously, you know that if that line is going uphill, then it's called a positive correlation, because it means that when one variable increases, the other variable increases. Okay. Now, in general, we have the independent variable on the x-axis and the dependent variable on the y-axis. The independent one is the one that kind of you can kind of fix in a way. But in some cases, we can't really have an independent and a dependent. So it doesn't really matter which way around they are then, to be honest. Okay. So they've got an example here of fitness levels. Okay. And the hours spent exercising. So obviously the hours spent exercising, you can kind of influence that. You can change that. And then you're interested in what's the fitness level. And there does seem to be a correlation here between, the more you exercise, the more your fitness level goes up. And there does seem to be a linear pattern. If there's a linear pattern, it means basically for every extra hour you exercise, you can predict how much your fitness level will go up by, because it's always going to be going up by the same amount. Okay. Now negative correlation obviously is the other way around. When one thing goes up, the other thing goes down. Same thing as before. Okay, sometimes of course we just get a random pattern, and that means there's no correlation, obviously. So here we've got an example of age and number of pairs of shoes. Okay, so age along the x-axis, because that you can vary that and choose different people of different ages, and then you're basically checking how many pairs of shoes they've got, and obviously it's completely random. And I don't know why there would be a pattern between age and shoes, but yeah. Anyway, so obviously you realize as well that we have descriptions of these. So obviously the closer it is to a line or to a pattern, then that's going to be strong positive correlation. Okay. In fact, this one looks kind of like very strong to me, because it's almost all on a straight line. And then we have moderate and weak. Okay. So generally they ask you to describe the correlation. So if it's 2 marks, then you need to say strong positive or whatever, or weak positive. Okay. The same with the negatives. Obviously this is strong or very strong to me, that one. This they're saying is moderate. I would say that's more like a strong to me, but anyway. And then this is obviously a weaker one where there is a pattern, but if you were to draw the line of best fit, then the points are kind of further away from that line, so it's quite weak, but there does seem to be a pattern. Obviously, if you on a line, on this one, if there's a strong one or a very strong, all the points are close to the line, which will mean that if you use the line to estimate values, it's going to be a good approximation, generally, because all the points are close to the line. So whereas with this one, the line that goes through the middle, there's quite a lot of variation. So your estimate from the line is not going to be as good. Okay. This is one thing to watch out for in projects, because what a lot of students do is they have a situation where there's not much correlation or very weak correlation. This one's probably no correlation. But they still work out the equation of the line of best fit. Okay, but you will be marked down for that, because although the maths might be correct when you finding the equation of the line, because there's no correlation, there's no point finding a line actually, because there's no correlation. So why would you want to have a line of best fit? Okay, so that's something to watch out for. Obviously we have linear ones and some other patterns we could have as well, other correlations. Okay, okay, so that's just a quick summary of what you should have done for IGCSE, and carry on with that. So here's some real life data actually. This is quite old data from 1960s or 1960. Cigarettes sold per person in the United States, okay, and lung cancer deaths, okay, so per 100k of population in different states. And you can see there is some correlation here. So it's showing that there's something going on, obviously, between cigarettes and lung cancer. So yeah, because originally they didn't know that there was a connection between smoking and health problems, and it was only the kind of statisticians working it out that showed that there was something correlation going on, and then scientists obviously proved there was a link. Okay. Now, one important thing, especially for your projects, is this thing about correlation and causation. Okay, now if we see that there's a pattern in the data and it's all the points are close to a straight line, then that's called correlation. Okay, but it does not mean necessarily that one variable is affecting the other variable. Sometimes there is a third variable or something else kind of happening. Okay, and here's an example. We have, this is real data from United States, fresh lemons, number of fresh lemons imported, and highway fatality rates, okay, for different years. Now, this looks like it's a strong correlation. Yeah, because they're close to that straight line. And but obviously there can't be, well, the more lemons you've got, it looks like the less accidents you have. Okay, so there is correlation because of the graph, but there's not what we call causation. The extra lemons cannot be causing less deaths, unless kind of eating lemons kind of improves your eyesight or something like that, but that'd be unusual. So you can see it doesn't make any sense in this case. And in fact, when we look at the reason, actually I put the reason underneath. It's just actually a coincidence that this correlation occurred, because what was happening was the US population was growing and they were importing more lemons to kind of for everybody, but at the same time they were introducing road safety measures that reduced the number of road deaths. So it was kind of totally unrelated, but the fact was that the number of lemons were going down and the number of deaths from car accidents was also going down. So when you plot them against each other, it looks like they're affecting each other, but they're not. Yeah. So we have to always be careful that, okay, we've got correlation, but does it mean actually we've got causation? Is one causing the other one? Okay, so that's something to watch out for. You would need some other evidence to kind of prove some causation. Okay. Now, I thought I'd use this example here. It's quite interesting. Does sitting at the front in a classroom improve your grades? Okay, there have actually been done some studies done on this, and they've had different conclusions. Let me just show you. So, oops, yeah, not this actually. I'll just give you a new page here. Sorry, it's a bit of listening at the moment, but later on we'll do some kind of activity. But if I draw it, get this thing to work. So basically, if this was the position that you sit in the class, okay, and this is your grades, okay. Now it could be that you sit in the first row, second row, third row, fourth row, or fifth row in a class, yeah. And imagine this is your grades, yeah, or percentage in a test or whatever. Now it could be that that when you plot the grades, it might look something like this. Obviously, it's not going to be perfect, but yeah. So the idea being that if you sit in the first row, your grades will be higher, and if you sit at the back, your grades would be lower. Okay, something like that. Now, I'm not sure that's true in our school, but I mean, it could be. And if we go back, there's some various things that we could think about. Maybe it is the position that's affecting the grade. So basically, all you would have to do if you wanted to improve your grade is go and sit at the front, because that's the factor that's going to give you good grades. Yeah, sitting at the front. Now, why would that happen? Well, maybe you can see better. The teacher asks you more questions. I don't know, but this kind of seems a bit unlikely. But I mean, it's possible. The other possibility, of course, is that the grades affect the position. So, in other words, if you get a high grade, okay, you want to sit at the front, yeah, and if you get a bad grade, you want to sit at the back to kind of hide. So it could be the other way around, that actually it's the grades that are causing you to sit in a position, rather than part A, which was your position, is affecting the grade. Yeah. Now, of course, probably A and B, I don't know, it's unlikely for these to be true maybe, but there could be this third variable. And the third variable in this case could be the student's level of motivation. So if you are a highly motivated student, you're going to get high grades, but you're also going to want to sit at the front, yeah, because you want to hear properly and you're keen and that. And the students who are not so well motivated, they're going to get maybe lower grades, and maybe they're going to want to sit at the back. Yeah, so that's the idea here. Perfect. Yeah, that's it, isn't it? Yeah, it's the rain, isn't it? Obviously, if that's the reason why people are buying the umbrellas, is the rain. And obviously, the more rain there is, then the more accidents there's going to be, basically, road accidents, yeah. Because the road's more slippy and people can't see as well. So it's not the umbrellas that are causing the traffic accidents, obviously. It's the third variable, the rain, okay. The fact is that basically chocolate is like a luxury item generally, isn't it? In theory, the more well-off a country is, the more chocolate that they would consume. Okay, and also, obviously, in the richer countries, they spend more on their education systems. So in theory, kind of. You'd expect them to have more Nobel laureates because they're spending a lot of money on their education, and at the same time, because they're a richer country in general, they've got a higher GDP kind of thing. They would eat more. They're going to eat more chocolate. That would be my reasoning, but there's kind of maybe some anomalies here because basically the nicer the weather. So basically the nicer the weather, the hotter it is, the more people are going to come out and eat ice creams. There's going to be more people eating ice creams. And actually, I think I read somewhere that the snakes, they come out more when it's hot. I don't know why. Maybe they come to like sunbathe or something, lie in the sun. But so the hotter it is, they kind of they like to be out, and maybe they're more active when it's hotter. So I would probably suggest that the third variable is the weather. It's the temperature. Yeah. Probably. So let's talk about this Pearson's product moment correlation coefficient. Okay. So the problem is, as you saw with the diagrams we had before, how do we know kind of what is high correlation, what's low correlation, whatever? So it would be good to have a measure, a mathematical measure of how good the correlation is. Okay, and that's this thing called the R value. And it's very good for working out if there is linear correlation between things. So it's not good for if there was a quadratic like pattern in it or whatever, or something else. This is for linear ones, so straight lines. Okay, and the way it works is it's quite nice. If the R value is 0, then there's no correlation. Yeah, or if it's close to 0, yeah, there's no correlation. If the R value is 1, that would be perfect correlation because all the points would be in a straight line. And if it's and that's positive because the line's going uphill. Yeah. If R was -1, then the gradient would be the gradient of the line would be negative, and all the points would be on a straight line. Okay, so the R value goes between -1 and 1. Yeah, 0, no correlation. Positive, it's a positive gradient line, and negative, it's a negative gradient line. And the closer you are to 1 or -1, the better the correlation is. Okay, so if you have a R value of kind of 0. Well, they're saying 0.75 to 1 is strong. Yeah, that's fair enough. But if you had something like 0.9 or 0.95, then the correlation would be very strong. Yeah, and it would be strong positive correlation. So how do we work it out? Well, we can use the formulas that I've skipped. Yeah, but like I say, you don't need to in the exam. The calculator always comes to our rescue. Will do everything for us. Okay, so I'm going to show you an example here. This is some data with the number of years smoking, X, and lung capacity. Okay. We're trying to throw in a few examples here to kind of put you off from smoking, I guess. So number of years, and you can see that the longer you smoke, it reduces your lung capacity, okay, which is not good. But if we want to work out the, let's get rid of this. So I'm going to show you on the calculator how to work out this R value. So ignore this because this came from previous example above. We're just going to we don't need this formula. The calculator will just give us the answer. Okay. So I don't know if you want to follow it or just watch it now. So we have stat. You go to stat, edit, and we need to clear the lists first to get rid of what was in there before. Clear, enter. And it's dead simple. You put the X coordinates or whatever one variable is in the first list. So I'll just do that. And in list 2, you put the other one. Okay. And then you always check that it looks the same because I've made millions of these mistakes over the years. And so it's always found it's good to just double check it. So that looks the same, doesn't it? Then you go to stat and you go across to calc like you normally do when you're finding the 1var stats, the statistics. But this time you go down to linreg, which is number 4. You click on that. Just make sure it says list 1, list 2, and the frequency list should be empty. So go on to that and then just press calculate. So here we have it, minus 0.962. Yeah, I've written it here as well. Okay, so that is the R value. So you can see that means it's very high. I would say, yeah, very high negative correlation because it's a negative number. So when it's a negative number, it means when one thing goes up, the other thing goes down, basically, yeah? So obviously this means that the longer you've been smoking, the lower your lung capacity. Yeah. Now this is a thing with the projects as well, that you have to relate if you do a project on something like this, you have to relate your results back to real life. So if you put this is very high negative correlation, okay, it's correct. But you also have to make a statement about what it means in real life. So you have to actually put a statement like, the longer you've been smoking, the lower your lung capacity. Yeah. Okay, this thing right now, what it is hopefully you can see at the bottom there. This is the R value showing, okay, with these points. I just wanted to show you kind of how it works. So if I put this is my data, these green points, but I can kind of move them around. So I'm going to try and move them around so that they're in a straight line, approximately. So can you see, the closer they are to a straight line, then the closer it is to 1. Yeah. Now it doesn't look like I can get them exactly 1 because, oh, there we go. Perfect. So all of these points are on a straight line. Okay. Now one of the things we're going to be looking at again later is these outliers that we were talking about before. So imagine one point is an outlier that doesn't really fit the rest of the data. We can see what happens to the other point. So let's choose this one. Let's say, can you see if I move that further away, it really wrecks the thing because everything else is on a straight line, but this one is not on a straight line. And now the R value has gone down to 0.55 just because of this value. And this value could be some kind of outlier or kind of mistake, yeah, in the data. So again, it's important to remove this point, because if you remove it, then obviously you'll get a true indication of what the correlation is. Yeah. Otherwise, you're going to get these really. And look at that. I can move it over to here. Where was I a minute ago? And it's really, really low. Yeah, like 0.09 now. So this is suggesting with this point down here that there's no correlation. But because this point is just kind of a strange value that doesn't really fit with the rest of the data, could be probably a mistake. It's looking like there's no correlation when actually there is very strong positive correlation here. Yeah. Now I just wanted to show you as well that obviously the further you get away from the, if you move these points away so that they're not all on a straight line, you can see the difference it makes. So something like that, it's still pretty high actually. Look, the R value is 0.933, so pretty high. But obviously the further apart these points get from a line through the middle, then you can see the R value is going down. I mean, here it's still okay, 0.8, so there is some correlation. But obviously if I move them around so that they're a bit more spread out, it gets less and less. And then eventually, if it's kind of randomly distributed, you can see it's getting closer to 0. Yeah. Yeah, the lowest, well, I don't know if I can get, oh, you see there, if I move that, that's pretty much on 0, isn't it? Yeah, like that, so totally random. So the closer it is to 0, there's no correlation. And obviously if I have the line kind of, if I move it so that it's going like that, you can see that already it's a negative correlation because it's going down. And then the closer the points are together, it's more closer to -1, yeah. And then obviously eventually if I you see that even that's minus 0.99, so very strong correlation. And then if I try to get them in a straight line, I don't think it's going to work this time, then it's not going to work, but you can get the idea. Yeah, eventually it would get to -1 if there was perfect negative correlation. Yeah, and again, if I have an outlier, it totally wrecks the results. And if you have 2, it doesn't make a huge difference. Well, it does, yeah. Yeah, so you get the idea. So we have to remove the outliers if there's any strange bits of data. Okay.